Okay, let's go. Our second speaker for the day is Bryce Clarke, talking about the free tabulator completion of a double category. Take it away.
Okay, thanks, Giacomo. Thanks to the organisers for this opportunity to speak at Ithaca. And thanks everyone for coming. So, okay, I want to talk about the free tabulator completion of a double category. And so if you haven't seen what a double category is before, then you should at least know that it has four kinds of things. It has some objects, some type morphisms, some loose morphisms, and some cells which have a boundary like this. And I'll come back to this in the next slide. And that a double category can also be seen as some kind of pseudo category object in the two category cat. Okay, so we have some kind of diagram like this in cat, and we can view this or understand this as having, a D0, a category D0, which is the objects and type morphisms of our double category, and a category D1, which is the loose morphisms and the cells of our double category, and some other stuff that isn't really important right now. And so what I want to do in this talk is sort of maybe discuss or consider two kind of basic questions. The first is that how can we reduce limits indexed by a double category, J, okay, to limits just indexed by a category, say I. Okay, so we're doing this process of taking something sort of complex, which is limits by a double category, and reducing it to something much simpler, which is limits indexed by a category. And how might we go about doing this? Okay, so that's one question. The second question is, can we understand the span construction as a right adjoint? Okay, so it's sort of well known within at least the double categorical literature that the span construction can be seen as a left adjoint in a suitable way. It's freely adding companions and conjoints in a sense. Okay, but can we also see it as a right adjoint? And we might like to do this for a variety of reasons. Perhaps one of those reasons is that we often want to consider, say, lax functors into span. And so if it was a right adjoint, we could sort of transpose this to some other kind of data. Okay, and so how I want to answer these two questions is using this so-called free tabulator completion. Okay, and that's going to be the aim of the talk today. So, again, if you haven't seen double categories before, perhaps you're already familiar with some other sort of two-dimensional categorical structures. And so if we have double categories up here, okay, they have sort of cells with a boundary like this, then we could simplify this in a number of different ways. Okay, one way we can simplify it is to get two categories by asking that all of our loose morphisms are just identities. Okay, so then you've just got objects, you've got type morphisms, which we can draw vertically like this, and then have some cells, alpha, that go from F to G. Okay, so this will be a two category, the underlying two category of a double category. And moreover, any double category that has all of its loose morphisms identities is the same as just a two category K, for instance. Okay, so that's one simplification we could do. Another special case of a double category are bicategories. Okay, and so this is where we do things in the other direction. So if we ask that all of our type morphisms are identities, then what we have left is just some objects, some loose morphisms, and some cells, alpha from P to Q, and this will give us a bicategory. Okay, the underlying bicategory of our double category D. And moreover, any double category that's of this form, where all the type morphisms are identities, is the same as some bicategory B. Okay, and then another special case we could consider is that of monoidal categories. Okay, and so this is just the same as bicategories above, where now we have just a single object in our double category, a single type morphism, just the identity on that single object. But now our loose morphisms can be considered as objects of our monoidal category, and the cells, say from A to B, can be considered as the morphisms in our monoidal category. Okay, and so I haven't told you, but probably you have understood already that in a double category, these cells can be composed in both the tight direction, so vertically, and in the loose direction, horizontally. And so that's how we get the two category and the bicategory structure here. And so for monoidal categories, the tight composition is just composition of morphisms in the monoidal category, and the loose composition is the tensor product in our monoidal category. Okay. So hopefully, at least if you're not familiar with double categories, you're familiar with some of these other special cases. And so if we want to consider some examples of double categories just to warm up, there's a few that I can tell you about. So for instance, if we have a category C with chosen pullbacks, we can look at the double category span C. And so here the objects are just the objects of C, the type morphisms are the morphisms of C. And the loose morphisms are spans of morphisms in C. And the cells are some commuting diagram like this, okay? And so the composition, the type direction is just ordinary composition in C, and the composition of spans is just done using our chosen pullbacks in C. Okay. Another example is rel. Okay, so here we have objects are sets, type morphisms are functions, loose morphisms now are relations, so they're subsets of the product. And cells are some kind of implication like this. If we have A is related to B via our relation R, then f of A is related to G of B via the relation S. Okay, and that's if a cell like this exists, it's the same as asking for this implication whole. Okay. Another example, another very important example is the double category dist. So here the objects are categories, the type morphisms are functors, the loose morphisms are distributors or profunctors or bimodules. Okay, so for me, distributor from A to B is a functor from A times B op into set like this, and the cells now are just natural transformations of this form. Okay. And another example is that if this is just something that I've been thinking about at the moment with the adjoint school group, is that if C is a restriction category, so some categorical encoding of partiality, then we can form a double category where we have loose morphisms are all of the morphisms of our category, of our restriction category C, and the tight ones are our total morphisms in our restriction category, and the cells exist if this equation holds. Okay, so that's just a variety of examples. And okay, this talks about the free tabulator completion, so I should tell you about what a tabulator is. And so what is it? It's if you start with the loose morphism P from A to B, the tabulator is a cell like this. Okay, so it's some object T of P together with some left projection pi of A, some right projection pi of B, and some cell like this. Okay, where the upper boundary is the identity. And okay, a tabulator is not just a cell like this, it's got some associated universal property. So the universal properties is that there's some bijection between any cell like this, so where we just have X up here now with some cell of boundary like this, and type morphisms into the tabulator object. Okay. And okay, what else can we say about tabulators? Well, tabulators are a certain kind of limit in a double category. They're limits of whose shape is just the free double category with a single loose morphism. Okay, non-identity loose morphism. Okay. We can also have a notion of cotabulator, which is just tabulator, but we flip everything in the tight direction, so vertically. Okay. Tabulators are natural with respect to cells, of course. Okay, so if we have a cell like this in our double category and P and Q have tabulators, then we get a type morphism between their tabulators. And lastly is that if we remember our pseudo category presentation of a double category, then D can be said to admit all tabulators if and only if this this functor here has a right adjoint. Okay, so this functor from D0 to D1 is takes an object to its loose identity morphism. Okay, and so if this functor has a right adjoint, then D has all tabulators. Okay, and so you can already see this adjunction coming up in this universal property here. This is, I guess, the instantiation of that. Okay, so that's what tabulators are. And maybe I should give you some examples. So first we'll look at examples in the special cases of double categories that I mentioned. So if we're in a two category, or a double category that's equivalent to a two category, then tabulators are just the same as powers by two. Okay, so again, remember that in this instance, all of our loose morphisms are just identities. Okay, so To give a tabulator is to give, well, some object, a to the 2, together with an identity morphism in a cell like this with projections, okay? And we can see this is a 2 cell going from pi 1 to pi 2, okay? And it has some universal property, which is to say that any other 2 cell from F to G in our 2 category is the same as looking at a 1 cell into this power by 2, okay? And so you'll recognize this as the universal property associated to a power by 2 in a 2 category. Okay. In bicategories, rather, it's a bit different. So in a bicategory, having a tabulator of a loose morphism P, well, first of all, the only tabulators that you can consider are of endo loose morphisms, okay, because the projections of our tabulators are forced to be identities. And this upper boundary is also an identity. So for a loose endomorphism in a bicategory to have a tabulator, this is exactly to say that there exists a unique cell from the identity on that object, okay, which is perhaps a bit of a strange thing to consider. But if we specialize again to monoidal categories, then this is just the same as saying that there exists a unique morphism from the unit object in our monoidal category, okay? And so in particular, if a monoidal category has all tabulators, then it has its unit is just the initial object. And if a bicategory has all tabulators, then it's just the co-product of a bunch of monoidal categories, which each have initial objects. Okay. And if we look at our other examples, then in span of C, for instance, the tabulator of a span P1, P2 from A to B, it's just giving us the X, the object in the middle of the span, okay, to go with the obvious projections and cell. In rel, it's again just giving us this set, which is the subset of the Cartesian product, is going to be the set which is our tabulator together with the projections. And in R of C for C, a restriction category, well, what can we say? Well, I don't want to say too much about this, but just to say that if our morphism in our restriction category has a restriction idempotent P bar, and this restriction idempotent splits, then the tabulator of that loose morphism exists and satisfies some extra two-dimensional universal property that I'll come back to later. Okay, so that's tabulators. That's some examples, so you know what I'm talking about. And we also have dis. Okay, so if we have a distributor from A to B like this, then what is its tabulator? Well, it's generalizing this category of elements construction. So you could imagine if A is the terminal category or B is the terminal category, and this is exactly giving you the category of elements of a pre-sheaf, for instance. And so more generally, its tabulator is going to have objects, which is just an A from A, a B from B, and some element in P of AB. And its morphisms from triples like this, you can imagine them as some kind of square like this that commutes, because it has to satisfy this extra condition that applying the action of F onto X prime is the same as applying the action of G onto X, okay? So that's what the tabulator of a distributor is. And again, you can easily see that this is specializing to the category of elements construction. And we could also look at the cotabulator. So just to give you a bit of a flavor of what cotabulators are like, if you have a distributor, then its cotabulator is giving you a cell like this in the double category dist, and its set of objects of the cotabulator is just the co-product of the sets of objects of A and B. And its Hom sets are, well, okay, we're just going to have the Hom set from A, we're going to have the Hom set from B, if the objects are from those categories, and it's going to be the set P to XY if X is from A and B, Y is from B, and it's going to be empty otherwise. And the composition of these Hom sets is just coming directly from this functorial action, this left and right action from the distributor. Okay, good. So, right, so we've talked about tabulators, but what we haven't talked about is Okay, tabulators is something of a loose morphism. In the double category, we can compose our loose morphisms. So I might ask the question, well, how does the tabulator of the composite of loose morphisms relate to the tabulators of each loose morphism individually? And so we could consider something else, which is a binary tabulator. And so this is, if we have a composable pair of loose morphisms like so, then we get an object T of PQ together with projection type projections pi A, pi B, pi C, and some cells like this. Okay. And there's this little lemma that's pretty easy to prove, which is that if you are in a double category that has tabulators, then admitting binary tabulators, okay, whatever these things are here, is equivalent to asking that we have pullbacks of our left projections along our right projections. Okay, I haven't told you what those are, but yeah, if we go back to tabulator, then okay, this is with respect to a tabulator, then pi of A is a left projection and pi of B is a right projection. Okay, so if we have pullbacks of those things along each other, then that's the same as asking for binary tabulators, assuming D has tabulators itself. Okay, and so here we can see in this picture that if we have the tabulator of P, the tabulator of Q, and we ask for this pullback here, which is assumed to exist, then we can construct the binary tabulator of this composable pair. Okay, and so the projection to A is just the composite here, the projection to C is the composite here, and the projection to B is the middle thing through this pullback. Okay, so and we can also say something else about binary tabulators. So the following equivalent, D has all binary tabulators. It has limits of normal lax functors from, this should be, no, 3. Yeah, that's right. Yeah, so from normal lax functors from the composable pair, the free composable pair of loose morphisms. Okay, and so because we have normal lax, these are giving us cells like this in our double category T. So we have limits of these things. And finally, we have right adjoints. Either one of these is sufficient to imply the other. Okay, so here we go from D0 to the composable pair of identity loose morphisms on an object, asking for that to have a right adjoint, it's the same as binary tabulators. And also from the fact that binary tabulators are the same as existing, of these limits existing, we have a right adjoint here. Okay, so this is just some technical stuff that I'm going to come back to in a few slides, but just to sort of put it out there. Okay, so we have tabulators, we have binary tabulators. Okay, good. What can we say? Well, how I want to tie this together is, first of all, with this span construction idea. And so just to introduce some terminology, an adequate triple is just a fancy way of saying a category together with a pair of wide subcategories, L and R, such that we have pullbacks of the L morphisms along R morphisms, and these pullbacks are stable. Okay, so if we pull back an R morphism, it again lies in the class R and so on. Okay, and so with this data of an adequate triple, what can we say? Okay, we have a two category of such things. Okay, sure. The morphisms are functors from C, which preserve each of the classes and preserve as well as preserve the pullbacks of L morphisms along R morphisms. Okay. And we also have a two category of double categories with tabulators and binary tabulators. Then, well, what can we say? We can say that, well, from every double category, we can construct an adequate triple. Okay, and so it's just going to be the underlying category of our double category, and the left class is this class of left projections. I mean, together with the stuff that you get from these pullbacks, together with the identities closed under composition, so it's generated by the left projections in some suitable sense, and the right class are the right projections arising from our tabulators in our double category, in our binary tabulators. Okay, so we need the binary tabulators here to get the existence of pullbacks of L morphisms along R morphisms. Okay, so we have this functor, this two functor like this, and we can get a functor in the other direction as it happens. So span is taking an adequate triple to the double category span of CLR. Okay, where now This is a bit more general than the span I just told you before, because we were just before assuming C was a category with pullbacks. Now we're assuming C doesn't have all pullbacks, but it has at least pullbacks along these two classes, L and R. Okay, so it's a bit more nuanced. And so now we get a double category whose objects and type morphisms are those of C, and whose loose morphisms are now spans where the left leg is in L and the right leg is in R. Okay, and we can see how these things compose and so on from the assumptions on this adequate triple. Okay, and so one can observe in a fairly straightforward way that these two things are actually adjoint to one another. Okay, so taking the underlying adequate triple of a double category with tabulators and binary tabulators is left adjoint to taking the span construction on an adequate triple. Okay, because every such double category of spans has in particular tabulators and binary tabulators. Okay, and right, and so here I've just displayed what the unit is. It's taking a loose morphism to its span of morphisms that we get from its left and right projection. Okay, so I've already sort of answered at least one of those questions I showed you on the first slide. Okay, that span is indeed a right adjoint, but one might instead hope to have span not land in double categories with tabulators and binary tabulators, but just all double categories, and wonder whether this also has a right adjoint. And it turns out the answer is yes. And so here is, I guess, the thing that I claimed in the title of the talk existed. And I sort of lied a bit, right? Because I said it was the free completion under tabulators, but what I really mean is freely completing under tabulators and binary tabulators. We need both of these things. We need the binary tabulators to get composites working in a nice way. Okay, and I mean, I don't even need to really show you this slide, right? Because if you've followed what I've said so far, you could almost really just guess what freely completing under this stuff should be, right? So, I mean, for every loose morphism in our double category, we add an object, which is simulating the tabulator, together with a pair of type morphisms, which are simulating the left and right projections, together with a cell, which is simulating the projection cell of our tabulator. Okay, so we need to add this stuff. Then we also need to have binary tabulators. So for each left projection and right projection, we need to add something which is acting like the pullback of these things. We need to have the universal property of the tabulators behaving as we expect it would. So we need unique morphisms into the tabulator identity, which satisfies these diagrams. We need something which goes from the binary tabulator to the tabulator of the composite of those things. Okay, so we add that in as well. And also for every cell, we need to get an appropriate morphism between the tabulator objects, and also one for the composable pairs of cells. We need to add that in as well, modding out by a bunch of equations that have to satisfy it. Okay, so you could have guessed this, and that's good. And so we get this adjunction here. And so what we can do is we can take this adjunction and compose it with this one that I had on the previous slide. Okay. But first of all, I want to say that if we have this double category, this free completion under tabulators and binary tabulators, let's denote its underlying category of objects and type morphisms, and we're going to call this L of S, LS of D, for what I want to call the loose subdivision of a double category. Okay. But yeah, coming to the point, if we compose this adjunction with the one I had on the previous slide, we can now say unambiguously that lax functors from any double category, rather than just one with tabulators and binary tabulators, lax functors from any double category D into span of something adequate triple are the same as morphisms of adequate triples like this, where L of S of D is this loose subdivision of D. Okay, and so in particular, if C is like is set, and L and R are just all functions, then this tells you how to sort of construct lax functors into span of set as some kind of functors preserving some classes of things. Okay, good. So that's one question down. What about the other one? I think we're doing okay for time. The other question is somehow motivated by this notion of limits. Okay, so if we have a functor of double categories from J to D like this, then we can look at cones over that functor like this, and the components of such a transformation of functors between double categories has components like this. Okay, and so I'm not going to really say more about what a limit of a double functor is more than this. But we have this nice theorem of Grandis and Paré, which is that a double category admits all limits indexed by any small double category, J, for instance, if and only if it admits small products, small equalisers, and tabulators. Okay, and so this really gives us a way to construct all limits indexed by a double category. And so how do they go about showing this? Well, the proof strategy is like this. If we're given a diagram F like this, then first we construct a new diagram I and some new shape I and some diagram G into the underlying category D naught. And we do this in a way using tabulators and binary tabulators. Okay, or at least implicitly, that's what they're doing. They then show that cones over the original diagram that we had of double functor is isomorphic to this category of cones over this new diagram that we've constructed. Okay, again, this is not exactly what they do, but it's more or less what they're doing. And then once we have this, by this classical result that all limits of functors exist if and only if a category has products and equalizers, we get the result that they claim. Okay. And so this is all very good. But if you look at their original proof, it's like 5 pages long. It's very explicit and detailed. And one might ask themselves if there's maybe a more abstract proof possible to show this result. And so that's sort of maybe one of my motivations for looking at this. And so something we can already say, just from what I said on the previous slide about free tabulator completion, is that, well, if we have a double category D that has tabulators and binary tabulators, then we know that double functors like this are in bijection with double functors like this. Okay, so certainly the categories of cones over these two things are isomorphic. But okay, this here isn't f of j is still a double category. It's not a category, right? But what we could do is pre-compose it with its underlying the functor from its underlying category of objects and type morphisms, okay, which is a category. And well, if this is initial, then the resulting thing will be something from a category into a double category, which is the same as from a category into the underlying category of objects and type morphisms of that double category. And then we're done, right? Okay. And so the trick is to show that this is this thing here, this inclusion of L of S into its double category, its free tabulator completion of J is actually initial. And I personally don't know enough about what it means for a double functor to be initial to show this directly. I mean, one could guess, right? Like one could say, well, the component between the D naughts and the component between the D1s and the component between the D2s and so on of the pseudo category presentation of the thing, each of these has to be initial as a functor, and we know how to check that pretty easily just by using some connected components stuff. And indeed, if one shows that for this, then it's pretty easy to check. But I don't know enough about that, so I want to come up with maybe another way to show this this is initial, or at least that we have that this L of S of J is giving us an appropriate category that we can replace our limit with. And so how I did this is as follows. So first I want to tell you about the nerve of a double category quite briefly. So we have the simplex category delta, and from each K in delta, we can construct a double category, which is just the free composite of loose morphisms of that length. Okay. And so given such a thing like this, we can get a nerve, okay, from this two category of double categories and normal lax functors. It doesn't really matter what the morphisms are, into simplicial objects in cat, okay, which is just given like this. Okay, this is just the internal HOM, the category of DBL and L. Okay. And so, for example, if we look at the 0 level, we just get the category D naught of objects and type morphisms. If we look at the first level, we get loose morphisms and cells. And if we look at the second level, we get, well, a category whose objects are cells like this. Okay. And so, okay, so a theorem is that this nerve is too fully faithful. Okay. And I mean, I haven't really proved this, but it more or less follows directly from the same result for bicategories. Okay, so Lack and Howley have this paper called the two nerve for bicategories or something like this, and they show that nerve for bicategories is too fully faithful. And you can essentially repeat this proof for double categories because it doesn't really rely on any significant way on the fact that they're working with a bicategory rather than a double category. So, okay, that's good. And so, okay, we had this two fully faithful nerve, and we could restrict rather the simplex category to just some smaller piece of data, which I'm calling D for now, and that's just consisting of these objects and these morphisms. Okay, and so a small lemma that one can prove is that this inclusion now is locally fully faithful. Okay, so what I mean to say is that if we have this data induced, if we have a double functor from J to D, and we have this data, and we have an F1, and our F's and our G's, then to have a two cell between these things is just the same as to have a transformation between the original double functors. Okay. Okay. Good. So what? And so what we can say is that the loose subdivision of a double category J is the colax colimit of this so-called truncated nerve, this thing that I just showed you here, okay? So if we just look at this data of a double category, and this J2 could be replaced with this other thing, it doesn't really make any significant difference. I'll just use J2 because it's simple.
Wanted to mention that you're entering the question time. So
okay, I'll wrap up after this slide. Thank you very much. Okay, so we could look at this data and look at its colax colimit, and we get exactly what L of S of J is. Okay, so this is a very nice abstract presentation. We can also note that if D has tabulators and binary tabulators, then we get a bunch of two cells like this just from the unit and co-unit of these adjunctions presentations that I showed you for tabulators and binary tabulators. Okay, so it's also providing some kind of colax cocone over some truncated nerve of the double category D. And so then we just say, well, by the universal property of colax colimits, each normal lax functor from J to D induces a unique functor from L of S of J, from the loose subdivision of J into the underlying category D naught. Okay, so we have the data of our normal lax functor like this. We paste it with this data here for our double category with tabulators and binary tabulators. We get a colax cocone, and then we apply the universal property to get the unique thing out of L of S of J. Okay, and then we can just use local fully faithfulness of this truncated nerve to show that the cones over this new thing that I constructed by this universal property are in bijection with cones over the original thing, and conclude that that the limits of these two things, if they exist, one exists if the other does. Okay, and so here we've just used universal properties. We haven't had to do any explicit calculations or determining what these functors are, and it fits in a slide rather than 5 pages. And I think I had some other things to say, but I'll just skip to the summary slide and finish there. Thank you for your time.
Thank you. Okay, are there questions or comments?
May I have a question?
Sure.
Ciao,
Yes,
Brian.
yes, Pino. Yes.
Thank you very much for your talk. It was very pleasant.
Thank you.
Just a simple question, possibly. You definitely suggested that your tabulation completion had some kinds of double limits. Usually, in the one-dimensional case, you perform a completion by cutting away from the resheaf on a category to obtain a completion with respect to certain colimits.
Right.
Can you do something like that? Yeah, of course, you have to oppose everything and do colimits first and then reverse.
Yeah, that's a really good question, actually, that I don't know the answer off the top of my head. Yeah, if you want to complete under, say, cotabulators and binary cotabulators, is this some kind of yeah, cutting down of some pre-sheaf stuff? Yeah, it's a really reasonable question, and I don't have a good answer for you, but thank you.
I'm looking forward to an answer.
Okay, thank you.
Thank you.
Anyone else? Do we know if tabulators exist in the double category of enriched distributors? Do you know?
Sure, if V is not, I mean,
V is
V
good.
nice enough.
Okay.
A lot of the time they don't.
Okay, because I've seen that for set distributors, it's the category of elements. So that's one of the things that doesn't generalize very easily.
Yeah, that's right. I mean, you need quite a nice V, I think, in general to
Okay.
get it.
Okay. Thanks. Okay, if there are no other questions, let's thank Bryce once more.